History of Vector Analysis, Episode 18, Modern Vectors, Part 2. You are here. Hey, it's old Doc Goler, and this is Part 2 of my climactic episode on the history of vector analysis. In one chart, last time I reiterated how Hamilton started with his IJK product rules for these imaginary parameters and then derived this key expression for the multiplicative product of two zero real quaternions. Then I showed you how Gibbs and Heaviside independently invented 3D vectors with no imaginaries at all, and then defined what we call the vector dot product and the vector cross product to match up with the parts of Hamilton's expressions on a term-by-term basis. Except for that minus sign in front of the dot product and, the definitions of IJK. Then, according to me at least, even my historian Michael J. Crow didn't want to say this explicitly, but it sure looks like what happened. Then Gibbs and Heaviside worked backwards to come up with the now real IJK product rules for the math to work out if you treated both dot product and cross product as a form of term-by-term multiplication. Okay, I'm going to come to a full stop here and discuss three implications of what we just did. In Hamilton's math, capital Q, shown in the box, was a quaternion, one that could be expressed as the sum of two components, what he called the scalar part and the vector part. If you recall, Hamilton showed that quaternions, while they did not obey the commutative law, did obey the associative law and the identity/inverse laws. But here's the thing. Individually, the scalar and the vector parts are not quaternions. Individually, these components do not, in general, obey the associative and inverse laws. What does this say about the vectors of Gibbs and Heaviside? It means we're in some trouble, that's what. One thing we may observe immediately is that in modern notation, the vector dot product is a scalar, while the vector cross product is a vector. Scalars and vectors are different kinds of mathematical objects. You can multiply different kinds of mathematical objects, but you can't add them. The operation of addition is not defined between a scalar and a vector. In vector math, this plus sign here and here does not exist. The same argument holds for the sum of the divergence and the curl of modern vector fields. Another implication is that neither the dot product nor the cross product are, at least in my view, truly multiplication, although this term is often used. Rather, I would argue they are two new and different operations. It is true that if you define vectors in terms of their xyz coefficients along the IJK unit axes and follow the IJK product rules that we just defined for them, the math does work out. Still, consider this about the dot product. Every time we have multiplied two mathematical objects of the same type together before, positive numbers, real numbers, complex numbers, the product was always in the appropriate set, positive, real, and complex respectively. The rule held for quaternions as well. The product of two quaternions was always another quaternion. Now, however, we find that the vector dot product is not in the set of vectors. And that cross product. I'll skip the part about how the cross product of two axial vectors is actually a polar vector, which is not the same thing as an axial vector. Story for another time. Let's just say for the moment that a cross product of two vectors is also a vector. Here's the thing. If you cross a non-zero vector into itself, which what I would call squaring it, the product is always zero. If the square of a non-zero vector is always zero, I would argue that there is an issue with referring to the squaring operation as a form of multiplication. In my personal view, it's better to think of the dot product and the cross product as new and different operations defined in addition to multiplication. In my view, the true multiplicative product of two vectors is defined, albeit with yet another set of IJK product rules. The result looks a lot like a tensor. All that's just my 2 cents. A third implication that I want to point out, in part because no one else ever does, is that when we define, del cross V as this series of terms, we are using the word define in a way that is different than how mathematics has historically used this word. Traditionally, mathematicians have used the word definition to formally recognize axioms or postulates. Examples are all right triangles are defined as being equal. Parallel lines are defined as those that are infinitely long but never meet. I is defined as the square root of -1. Definitions are rules that we can't derive, but are in some way or another obvious. What we are doing here is different. In the case of this cross product here, we are truly just making the definition up out of whole cloth. Hamilton justified his definition of quaternion multiplication in terms of what he at least believed was some sort of truth, his IJK product rules. Gibbs and Heaviside have no such compunction. They propose no truth that the dot product and the cross product are derived from. They are completely artificial. Okay? In my view, this is actually a metaphysical revolution in the history of mathematics. It is perhaps ironic that the metaphysical position of Gibbs and Heaviside is, in essence, there is no metaphysics, at least none that we care about. None of this is real in any external sense. Okay? It's sort of a kind of mathematical atheism. Let's take a step back and look what Gibbs and Heaviside proposed in this light. Philosophically, I think it is not inappropriate to ask the question, okay, what the hell just happened? To summarize, Gibbs and Heaviside brought modern vector analysis out of quaternion analysis by lightly modifying the stuff on the surface. They redefined I squared to be +1 instead of -1, and a few other changes like that. However, they simultaneously gutted everything underneath. Okay? They did this by separating the scalar and the vector parts of the quaternion, and then by allowing them, that is, requiring them, to operate by mathematical rules that are not only different from those of quaternions, but different from each other. This begs the metaphysical as well as the mathematical question, can you even do this? Can you just make up math? To use our maze metaphor, it appears that what we have done with the creation of 3D vectors is take a shortcut, okay, over, under, or through the constraints of the maze. Boom! Okay, how is this possible? Isn't this cheating? Okay, I don't think there's any way I can answer this question without getting into some external history and some metaphysics. I humbly ask you to bear with me. Anytime prior to the 19th century, I believe that the answer to this question would have been a resounding no. But the pressure of the Industrial Revolution and the orders of magnitude more wealth that it produced would not take no for an answer. Civilization needed mathematical models that worked, and people outside of the mathematical community didn't really care if those models were consistent with some modern or ancient vision of truth or reality. Okay, reality now was, I need to deal with this frickin' signal distortion problem if I'm going to invest a fortune to build this long-distance telegraph network. Okay, or we need to get real-time communications from our land-based headquarters to our warships at sea before the enemy does if we are to maintain our position as a global power. So the quick answer to the question, can you do this, is sure, of course we can. Okay, man's original metaphysical goal with regard to mathematics may have been to, understand the mind of God, but over the centuries it would appear that at least some math is of mortal human origin, and we humans are free to do what we want, or more to the point, what we need when it comes to constructing a mathematical system. The older question for mathematicians was, does this mathematics represent external reality? Is this how the universe truly works? Okay. This question has now, at least in some circles, been replaced with two new questions. The first is, what are the rules of this new mathematics? What identities does its defined operations consistently obey? And second, is this new model useful? Okay. Can it help physicists and engineers model external reality, which we still believe exists, okay, but model reality well enough to allow practical progress? This, folks, is what an intellectual revolution looks like. Next, I want to briefly discuss how the community reacted to Gibbs and Heaviside's vector analysis. For a long time, no one reacted at all. Neither Gibbs nor Heaviside were famous at this time, and their publications appeared along with thousands of others that postulated all sorts of crazy stuff. vector analysis was barely noticed when it appeared. It came with its own learning curve requirements, and it did not have a big name to champion it. One person who did notice it was an older Peter Guthrie Tait, who was not at all pleased. After Hamilton's death, he had become the champion for quaternions and considered vector analysis to be a threat to the wider acceptance of the quaternion approach by the physics community, which in fact it was. Interestingly, at least I think, Tait didn't bother to argue against vectors on any sort of metaphysical basis involving capital T truth. I think he recognized that that ship had sailed. Rather, he argued that these Gibbs Heaviside vectors were lousy mathematical objects. Unlike quaternions, Tait noted, vectors did not follow the associative law under multiplication, and they didn't follow the commutative law either. Division was not even defined for either the dot product or the cross product. There was no scalar vector coherence. Okay, I'm going to talk more about this in the remaining episodes. In short, Tait argued that these new vectors were a mathematical abomination. The fact that Gibbs, who had an academic reputation to protect, never formally published his notes on vector analysis, may be due to the fact that he tacitly agreed with Tait's objections. In many ways, vectors were and are lousy mathematical objects. In response to Tait, by Gibbs politely and by Heaviside less so, perhaps because Heaviside had no academic reputation to protect, was, in essence, okay, our vectors are lousy mathematical objects, according to pure mathematicians. So what? Okay? They are useful to working physicists and engineers, and we believe that that is sufficient to develop them further and to encourage their use, even over quaternions. Heaviside, in his major work Electromagnetic Theory, wrote publicly and bluntly about Tait's quaternions. Quote, "If we put aside practical applications to physics and look upon quaternions entirely from the quaternionic point of view, then Professor Tait is right, thoroughly right, and quaternions furnish a uniquely simple and natural way of treating quaternions." Observe the emphasis. Okay, in Victorian England, this was some serious trash talk. Meanwhile, once the new vectorial approach started to become known, Cartesianists attacked them as well for the same reasons that they attacked quaternions. They were completely unnecessary. Arthur Cayley championed this faction rather than William Thomson, but like Thomson, Cayley argued that both quaternions and vectors offered some clever abbreviations, but neither saved any labor when calculations were called for. Historian William Crow discusses the debate that raged via articles and letters to the editor in various major scientific journals over a decade or so in some detail. One of the advantages of this debate, Crow notes, for the vectorists, was that it brought a lot of attention to their approach that they wouldn't otherwise have received. It also made Gibbs and Heaviside more famous within certain important, if esoteric, circles. That brings us to the end of this long climactic episode. In the next episode, we will start the all-important mopping up process. I will take a step back and talk about the algebraic properties of vectors, the dot product, and cross product. We wouldn't want to leave any of that out. Of course, in some ways, this will be the heart of the matter. Rules governing mathematical objects that we actually, use today. At any rate, see you then.